Okay, in this video, we are going to look at composite functions, both how to calculate a composite function and how to find the domain once you've figured out what that composite is. We'll start with just the composite functions, and just real briefly, I have the definition up here at the top. When we are finding composite functions, we are using one function as the input to another function. Okay, and then here you'll see the notation for composite functions. It's that little circle. That little circle in the middle. Usually we would read this as g of f of x. F, that comes first, that's what I'm going to refer to as your outside function. And g, the one that comes second, that's what I'm going to refer to as your inside function. So for this first line, this is taking the function f and using g as the input into that function. Or we could switch the order, g of f of x. Order matters here. This one, g of f of x, is usually not going to be the same as f of g of x. And the second line here, g is the outside function, f is the inside function, f is the input to g. So one thing to think about here, I think people don't feel real confident about function notation, so that makes a problem like this a little tricky. Remember that when we see this f of x equals 3x plus 5, remember that means f of some input is equal to 3 times whatever that input is, plus 5. Okay, that's another way to think of this, what this function notation means to us. So before we do the composite, let's just practice our function notation real quick. Here, f of 1, that means we're going to take 3 times 1 is our input, plus 5. So 3 plus 5, that would be 8. Similarly, f of 0, same idea, 3 times 0 is our input, plus 5, which is just equal to 5. We could have an expression in that parentheses as an expression as our input, which we had this type of thing when we were working on our difference quotients. But in this example, x plus h is our input. So if 3 times the quantity x plus h plus 5. There's not a lot of simplifying we could do there. We could distribute that 3, although we don't end up with any like terms. And then finally, we get down to our composite. Same idea. We're taking our function f, and we have an input for it. Our input is g of x. So we're going to have 3 times g of x plus 5. Except the difference here is that g of x is an entire function that we have listed over here on the right. And so we can take this function g of x and put it right in here into our composite. So 3 times g of x is x squared minus 1, so plus 5. Here we will distribute because we can do a little combining of like terms. We get 3x squared minus 3 plus 5, which is 3x squared plus 2. And that is our composite, f of g of x. So if I wanted to label it, there it is. There's our composite. Okay, so we're going to try a few more of these. It can get a little trickier if your original starting functions are a little more complex. So here's example number 2. And we have a f and a g that are given to us in the problem, and they want us to find f of g and g of f. So let's start here, f of g of x. And I always recommend writing out that definition. I think it's going to be easier if we write it out like this in our function notation. So this means we're going to look at the function f, and we're going to use g of x as its input. So our f says the square root of our input, which is g of x, minus 3. Okay, notice that follows the exact function we have up here for f, just instead of x, we now have g of x. And we can simplify that even further because we have g of x. It's over here given to us. G of x is x squared plus 4. And then we still have that minus 3 hanging on there. And now we can combine some like terms. So we end up with x squared plus 1. That is our composite function, f of g of x. Okay, we can also take it in the opposite direction and do g of f. This pen's a little thicker, sorry. G of f of x. Okay, so now g is on the outside and f is our input. Okay, so start and find out what function g is. G is x squared plus 4, but instead of our x, we're going to have f of x. That's our input. Input squared plus 4. So that was using g of x. Now we can simplify it by plugging in our function for f of x. So f of x is the square root of x minus 3. We still have that exponent of 2 plus 4. On this one, we can do some simplifying since we have a radical and an exponent there. Those two kind of knock each other out. We end up with just x minus 3 plus 4. And combine our like terms, x plus 1. So that is our composite g of f of x. Okay, let's look at an example that has some rational functions in it. We have some fractions here. And again, same directions, find a little bit different. We're going to find f of g, and then we're going to find f of f. We can use the same function as both the outside and the inside. We'll see how that goes. So f of g first. That means we're taking f of g of x. G of x is our input into the function f. So start by finding that function. Where's f? Right up there at the top, 5 times whatever our input is over our input again, minus 3. Okay, so that was applying our function f with g of x as its input. And then we want to go ahead and we want to put that g of x function in there. So we have 5 times 4 over x plus 2 all over 4 over x plus 2 minus 3. So you can see when we have a composite with these rational functions, we do end up with a complex fraction. So we need to go ahead and simplify that a little bit. The easiest way to simplify this one is going to be multiplying the top and the bottom of that fraction by x plus 2, because then we can cancel out those denominators. So up top, let me scroll down a little bit so we have more room. Up top, when we multiply this x plus 2 and this x plus 2 cancels, we are left with just 5 plus 4. So there's our numerator, 20. On the bottom, since we have an expression over here with two terms, we need to make sure we distribute this multiplication. So when we distribute it with our first term, it again cancels. X plus 2 cancels with the denominator. We're just left with 4. And then we have our minus 3, and then there it is distributing to our second term, x plus 2. And then this is a lot simpler, but we can still do a little more cleaning up. We get 20 over 4. We'll distribute that negative 3. And then combine those like terms in the denominator. We get minus 3x. A plus 4 and a minus 6 gives me minus 2. And that is our composite f of g of x. With these same two functions, let's take a look at f of x. Use different color here. Okay, this time f is the outside function and the inside function. Procedure is the same, we just gotta keep everything straight here. So we start with the function f, and f says 5 times your input, which in this case is also f, divided by your input, minus 3. Okay, that was applying the outside function. Now I can go ahead and substitute the actual value, the actual function of f in here, 5 times 5x over x minus 3 over, we have our function f again, And we still have that minus 3 at the end. And again, same procedure we did before. We want to cancel out these denominators, so we'll multiply the whole thing by x minus 3 over x minus 3. Up top, we get some nice canceling going on. Those two cancel. We are left with just, 25x. Sorry about that stray mark in there. Let's see if I can erase that. We'll just start that again. So we get 25x on top. On the bottom, again, distribute it. It cancels with the first term, and we just get a 5x. And then with our second term, we get that minus 3 times x minus 3. Go ahead and distribute on the bottom. And finally, we can combine those like terms. 5x minus 3x leaves us with 2x plus 9. There is our composite f of x. Okay, now that we've had some practice finding composites, now we need to talk about how to find the domain of one of these functions. And when you have to find the domain of a composite, you really have to find two different things. You have to find the domain of the original inside function, and you have to find the domain of the newly created composite. We're going to take those two domains, put them together, find the intersection, and that's the domain that we are looking for. Okay, so let's look at some examples. These are the same composites we just calculated. I just copied those problems down again. So our first problem that we did, example 1 in this video, was f of x, g of x, and then this was the composite that we found. Okay, if we are asked to find the domain of this thing, we need two pieces. We need to find the domain of the original inside function. So that's always going to be the one that comes second in that composite notation. So first thing we need is the domain of g of x. And this one, our g of x over here, no even roots and no variables in the denominator. So we don't really have any restrictions on this domain. The domain of g of x is just going to be all real numbers, or in interval notation, negative infinity to infinity. And then we need to figure out what the domain is of that new function that we calculated, f of g. Okay, we have that right here. And again, no even roots, no fractions to worry about. The domain of that function is also all real numbers. And so this one's pretty basic. When we put these two together, our domain is still all real numbers. Okay, so let's look at the domain of the second example we worked on. For example 2, here these were our two original functions, f and g. And this time I'm just going to do the domain of g of f of x. That was one of the composites that we calculated. Okay, so if we want the domain of g of f of x, we have to start off with the domain of f. That was our inside function. Excuse me. So up here is our original function f. This does have an even root. It has a square root. And we know that you can never take the square root of a negative number and get a real answer. So we need, for whatever's under that square root, to be positive or 0. So it's got to be greater than or equal to 0. Okay, so we take this little inequality, add 3 to both sides. That tells us that for the first part of our domain, we know x has got to be greater than or equal to 3. The second part of our domain is the domain of that composite that we just figured. And we have that one right here. This is what we calculated in example 2. This one, no radicals, no fractions. So this one has a domain of all real numbers. Now we take these two pieces and put them together. All real numbers doesn't add any more restrictions to us, so the domain of f really is just our final domain, x greater than or equal to 3, or in interval notation. The domain of our composite function is 3 to infinity. Okay, and then example 3 was the one we did with the rational functions in it. So again, let's find we'll find the domain of both of those. The domain of f of g of x first. Okay, start with the domain of the inside function. So domain of g. And over here is our original g of x. It was 4 over x plus 2. We do have a fraction here with a variable in the denominator. We know that the denominator can never be equal to 0. We can't divide by 0. So that means that the denominator cannot be equal to 0. Move that 2 over to the other side, and that tells us one restriction on our domain is that x cannot be equal to negative 2. And we also need to consider the domain of the composite that we calculated. And that one's right up here. Again, another rational function. So again, the denominator cannot be equal to 0. So we'll move that 2 over. Divide both sides by negative 3. We found out that x cannot be negative 2/3. Okay, so we have to put both of these restrictions together. So basically, in words, what we have going on here is that x can be anything, all real numbers, except for negative 2 and negative 3. When we put that into interval notation, we'd start at negative infinity, stop at negative 2 to kick that number out, and then continue on until we get to negative 2/3, and stop to kick that number out, and then continue on to positive infinity. This would be our domain of g of f of x. In this example, we also looked at f of x. So let's try to calculate the domain of that. Inside function is f, so that's what we need to look at first. And that's over here. Here was our original f of x. Again, a rational expression. So we get that x minus 3 cannot be 0, which means x cannot be positive 3. We need to look at the domain of your composite. And that's what we have right up here. So again, the denominator can't be 0, so that means that 2x plus 9 is not 0. Solve that for x. X cannot be negative 9 over 2. So again, in words, for this f of x, our domain would be all real numbers except negative 9/2 and positive 3. In our interval notation, start at negative infinity, stop at 9/2 to kick that number out. Continue on again until you get to 3 and stop there to exclude 3, and then continue on to positive infinity. That would be the domain of f of x. Doing the domain on these composites really relies heavily on you understanding the domain of these individual functions. So if you need to, go back and review that video. Once you have that down, it really is just putting 2 of the domains together into that final domain that'll give you your answer. Good luck!